Okay, great. So just a reminder, please turn off your mics and speakers or in this room. Okay. Our speaker today is who is Director of the Division of Geoinformatics at the Royal Institute of Technology in Stockholm. Before she was KTH, she was at York University in Toronto, and she received a PhD from University of Waterloo in Canada, which is a place which I really love because I was there 16 years. I didn't even realize she was Waterloo and her research has been focused on Earth observation for many years, and she's actually been heading the Pangea project, which has been the benchmark that we've been using in this group for quite a long time. She's been the recipient of many awards, including the 2025 Group of Earth Observation Lifetime Achievement Award and the 2023 Google Geo for Good Impact Award for her contributions to AI-driven Earth observation. Besides many other awards. And we're really delighted to have you here in person, and the talk is all yours.
Thank you so much, Chair, for inviting me, and it's really an honor to be here. Actually, first time in Cambridge, being UK many times, so it's really a pleasure to share the work we've been doing at my division. Specifically the project on how to use Earth observation and AI to monitor global environmental changes with some examples. So this project is funded by Digital Futures. It's a center of excellence in Sweden. The government gave us about 140 million Swedish krona per year to fund projects to support society's digital transformation. So this is one of the flagship projects. So yeah, as you all know, that our planet is facing multiple challenges, from melting sea ice to retreating of glacier, from drought, wildfires, floods, as well as pollution and emissions. So there are devastating economic, environmental impacts from fires, from other disasters. Urban is one of the critical challenge. We have many people are moving to urban areas. According to UN, 1.5 billion people are moving to cities by 2050, and the majority of the increase will be in Asia and Africa, where there's a critical need of data. Urbanization has many impacts, as you all know. And specifically, what the science found is that the impact of cities are under reported or evaluated to climate change. So that's why IPCC recently commissioned a new report on climate change in cities. So I'm on the review panel for the IPCC, this special report. So definitely there are many challenges in cities. So cities like Stockholm has a lot of data, but still the city complain they don't have enough data because they want to do sustainable planning based on changes either 2D or 3D as soon as possible. So that means we need to create a dynamic digital twin that we don't even have a good static one. But consider that rich cities in global south, you don't even have proper data. So there's a big critical need for urban data and other data in forests and floods, etc. So since 1972, many Earth observation satellites have been launched. They provide petabytes of data that can provide monitoring of Earth, on a global scale, daily with low resolution satellites, but every few days with Sentinel-1, Sentinel-2 is a split of satellites. So yeah, just to say that, we have a lot of data, every 10, 15 minutes on a global scale. Then at this scale, we have daily, sub-daily, and then we can even zoom in more than very high resolution at 10, 30 centimeters. So with the Earth version data, we can see annual dynamics of what's happening on Earth and also the vegetation change. Mostly in Africa, you can see the retreat of vegetation, seasonal changes, as well as river changing routes, deforestation, wildfires. And also the carbon monoxide measurements to track pollution. These are actually coming from wildfires in Canada. 300 million people were affected and fire came all the way to the UK and other part of Europe. Yes, cities are growing, so you'll see this before. But there are challenges. Let's say Stockholm, we have a lot of clouds, I guess similar to the UK, so therefore we're using multi-modal data, SAR, independent of can penetrate through clouds and take images overnight. So these are really useful data for monitoring purposes. SAR, I think a lot of you are working with forestry-related work, with the recent launch of biomass mission, P-band, and also NISAR by India and NASA. So L-band, they're all very useful for forest stand volume estimation, among others applications. So high resolution data like this one, 30 centimeter resolution, you can see a lot of detailed changes over time. So we are really in the era of Earth observation big data, many satellites. So it's expected we will have 724 monitoring every 15 minutes. Of course, in addition to the ethical issues and how do we deal with this kind of big data. So I think we have great opportunity for near real-time or real-time monitoring of phenomena affecting build and nature environment. And we have dense time series for analysis of global environment changes. We have new possibility for operational reliable services, but we need innovative computing infrastructure to handle, store, and process this data. We need new methods, algorithms to extract valuable information useful to decision makers. We need to integrate analysis of EO imagery with other geospatial data, social media, ground sensors, cloud-based data. Again, with AI for EO, there are opportunities. Foundation models you're developing here are definitely critical to, look for changes, classify things, monitoring. But how do we use AI in a responsible manner to accelerate variety of applications? Definitely it's something that my team have been focusing on, and I know all of you have been working with them as well. So this Global Change project, the main objective is really to develop innovative and also globally applicable. So not just, it works in Stockholm, in Europe, but it doesn't work in the global south. Actually, we want everything to work at a global scale, especially in the global south. We started with looking at urbanization monitoring, urban mapping and urbanization monitoring, and also wildfire monitoring. Then we expanded to flood mapping, as well as forest height analysis. So in this, basically, we look at variety of SDG impact and also Paris Agreement, Sunday Agreement. So this kind of research need an interdisciplinary team. So we have myself and my colleague Andrea Nassetti in remote sensing. Then we have Joseph and Sullivan and Hossein Azizpo from computer vision. Then we have Wula from environmental science. Most importantly, we work very, very closely with the stakeholders. City of Stockholm, Stockholm region, UN Habitat, they're all city users. Then we have Swedish Civil Contingency Agency, Forestry Authority, British Columbia Wildfire Services, and the Ministry of Forests. These are interested in forest fire monitoring. So urban, I will not talk about challenges, but urban mappings, look at the remote sensing data. We have Sentinel-1, SAR every 6 days, 20-meter resolution, Sentinel-2 every 5 days with 3 satellites every 2-3 days at global coverage, if it's not affected by clouds. Then we also have multispectral planet data. Basically, it's daily. We have access to the archives. Then we have MapSAR, less than 1 meter, but it's not free or open. The research gap includes how do you transfer deep learning model across geographic regions? Often the training data coming from data-rich regions in, let's say, in Europe or North America, they have the building footprint in the beginning, but not elsewhere. So we train using Microsoft building footprint, then we deploy it in globally. And the second challenge on the urban side is the deep learning-based multi-modal data fusion for change detection. So often you use optic data, SAR data. How do you bring them together to improve change detection? The third is really continuous change detection. This came from our stakeholder, City of Stockholm. Want anything changes, they want to know right away so they can incorporate that into planning. So we've been working on continuous change detection using satellite time series. Then another demand coming from Civil Contingency Agency is that there are a lot of disasters, floods, fires, hurricane, etc. So what kind of damage it has to buildings, different damage severity, how to track that and assess this different severity. We basically have more than 200 study sites around the globe, and we split them to training, testing, validation data sets. We used Microsoft building footprint and unit time process 1 and 2 imagery for urban mapping tasks. The basic model is just simple models. I will not talk about it here. So at the time, it's several years ago when we did this work, as I mentioned, we only have building footprint in North America and a few cities in Africa. So how do we, cities in different parts of the world have different morphology, how they are designed are different. So we decided to use unsupervised domain adaptation using unlabeled data in this mapping process, so that to improve the mapping accuracy, we only have one model. The data set we compare, the so-called stable arts, is generated by the European Joint Research Center. They have different regions, different model adapted to different geographic regions. So we had one model. Using domain adaptation, we managed to actually have comparable or better results than at the time. So there's some results. You can see Sentinel-1 and 2 at 10-20 meter resolution. We actually managed to extract very good building footprint. And we applied that, let's say, training in North America, right? So directly applied to Stockholm. You can see the high density build up in city centers and the suburbs, and also very sparse buildings were really well extracted. What happens in Beijing, and again, really good results. We also have in Dar es Salaam, compared to with the on the right-hand side, can get result with the JRC's global human settlements footprints and not do. Obviously, we are a bit better, a lot better. So anyway, so the idea is anywhere in the world, and we have an app. So you just choose your area of interest, and then any stakeholders or users, so that you can get images automatically, send one, send two, and then the model will be deployed, and you get building footprint. And then we don't have to map global buildings again if we have a good baseline. So then how do you track changes continuously? So this we also work with change detection algorithms. So there are some multi-modal biotemporal change detection. Basically, you have a pre and post, and you track changes. These are really a traditional way of doing change detection. What you get usually is annual changes. That even though Stockholm, it's not changing that fast. Actually, it's one of the fastest growing. If not, I think I saw it somewhere that it's the fastest growing capital in Europe. So there are a lot of changes going on in Stockholm. So yeah, that's why the city came to us to say, we want to know after we give out building permits, what's changed. Said, but don't you know? No, we don't know. We don't have enough people to go around to find them. So therefore, how can you do it using satellite? So that's what we started this 5 years ago. Then how do we do multi-temporal change detection? Basically, it's to look at the changes continuously. So this is a SpaceNet 7 challenge using monthly planet data. So what we trying to do is you design the multitask interaction for continuous change detection. So the idea is really to look at instead of biotemporal, you have multiple timestamps, and then you utilize all these in order to do change continuously. Change and not change, and planet, there are some atmospheric effects and some issues with the image, but we still manage to get quite good change detection. I think the result could have been better if we use more than RGB images. Since this challenge didn't really give the location data, so we couldn't really retrieve, let's say, the near infrared bands or other bands. With more bands and geographic location, it would have been much more helpful. I think this challenge, maybe they wanted to make it a challenge, so lack of information is a challenge as well. So then continuous change detection, the city say, oh, maybe we don't need every day or every few days. If you can lump sum it into, every 3 months, that's good enough. So that's what we did. So it's, we detected the, new buildings and demolished buildings as well. And in Beijing, Shanghai, in other parts of the world. Next, I'm moving on to multi-hazard building change detection. Basically, this is a XBD challenge, XBO2. You have pre and post disaster, very high resolution images. Again, these are RGB images. And also doesn't, it actually gives your location, but it doesn't give you much more other information. We would have preferred other bands as well. So you have building damage levels. Severely minor damage, no damage, major damage, and destroyed buildings from wildfires, volcanic activities, earthquakes, storm, and floods in different regions of the world. So you can see a lot more in North America than other parts of the world. So you have some imbalance. So yeah, so it's quite a simple model, but we sort of design a disaster adaptive network. The idea is first we take the winner's model. The winner has used like many tweaks and things. It's an ensemble of different things, very complex. So we basically simplified it to say, okay, we make a baseline model that is almost as good as the winners, but it's much simpler. So we use that model. Then we decided to put in the disaster information. We think these are readily available. You know what kind of disaster it is. You tell the network, it's more or less like an embedding. So that disaster type, and so learn memorable disaster embeddings, you add that disaster specific as a disaster specific efficiency into the model. So that seems to actually produce much better results. So yeah, some of the quantitative results we compared with different type of models and networks. So we have. Yeah,
would you like questions at the end or can we ask in the middle as well?
Pardon?
Would you like questions only at the end or can we ask now?
In the end.
In the end, okay.
Okay, oh, but maybe it's good to ask now since we're here.
Okay, could we go to the previous slide?
Yeah.
This looks a lot like a Barlow twins type model, right? Because you're having two different encoders, projector,
Yeah.
and you're sharing weights.
Yeah.
But then you're adding this feature adaptation in the lower arm. So I don't understand why you're doing that. That looks very interesting. What is that for? The feature adaptation.
You mean the disaster type?
Yeah.
Because what I want to explain is that we got results, some are without that disaster type information. You have some issues with the result. Maybe I can go forward to say, okay, if you don't give disaster specific data, so let's say this is a label, and these are wildfire damage, but this is basically a flood damage, right? So if you have it's storm and floods, you can see there much more. A flood and a storm is really floods, right? So they are much closer to the level than if you don't give any disaster information. So just with a simple disaster specific information, you improve the result tremendously. So it's just that's the motivation why we did it.
Okay, but wouldn't you make that an input into the ARM rather than putting it at the output in the feature adaptation layer? I mean,
maybe we should try that. We haven't tried it.
Okay.
We just thought, okay, this is just a simple thing you can do to improve the result. We're very much like application oriented. We said, okay, we do whatever that works.
Okay.
Yeah, but definitely we will try that.
Okay,
Yeah,
thank
good
you.
suggestion. Thanks. So yeah, so the next, so far we've been talking about mostly on 2D. Cities are not growing in 2D, but also in 3D. How do we use open data? Again, you know, some of you are using LiDAR, so cities are creating digital twins using laser scanning. They're quite expensive. Even city of Stockholm, they can't afford to scan every year. So they do 1/3 of a city per year. So in 3 years, they will have a full coverage. So for Global South, people can't afford it. We're thinking, okay, there's European cities with good laser scanning data. How can we utilize that using open data, sample 1, sample 2, to generate 3D, for the Global South or for other regions of the world? So as you can see, sample 2 during summer and winter, the shadows are different. Definitely, you can get 3-dimensional information from this. And also radar satellites ascending and descending, looking at city from different directions. That also provides some information. So with that, we thought, okay, let's try the Sentinel 2 for 3D mapping. So we were looking at large scale. Again, the JRC, European Joint Research Center, they have GSSL build height from 2023 at 100 meters. Then we have the DRR's German Aerospace Center's World Settlement Footprint 3D at 90 meters. Can we get 10-meter resolution using our method? So that was the idea, and how to do large-scale building height estimation using open and free data, Sentinel 2 trained in limited European cities. So basically, we have 4 countries and the data from 10 different cities. Then we have this deep learning model, Sven unit, if I remember correctly, and then we have LiDAR data, Sentinel 1, 2, and then we deploy it in different cities. So just to show the result, predicted height, and then the predicted segmentation. So you have the height and also the building footprint, and in the middle, that is the reference height. So that turns out, I think, quite well. Then, yeah, we were looking at the generalization in other domain data set, and the result also looking quite good. Then, yeah, we can do large scale, the whole city, and compare with, let's say, the 10-meter. We diluted our resolution from 10 meter to 100 meter. So you see the reference and GSHL, at the time, several art were much closer to the reference than their results. With this work, the German Aerospace Center, they have global data set. They want to do 4D global. So they have contacted us last year to say, can we work together, produce a global 4D data set, not only 3D. We also, with Sentinel 1, Sentinel 2, you actually have the time series you can work with. So now we're trying to produce global 4D data set together with the DR. Yeah, so we also work with some environmental impact of change, urban change, how urbanization affected biodiversity, urban rain, etc. We also compared, let's say, Stockholm with Beijing in terms of loss of ecosystem services, and looking at urban heat island, change over time. Cities are growing, city centers are getting hotter. Floods, how to do rapid flood mapping. This was Hurricane Idai, not hurricane, what is Cyclone Idai. In Beira, Mozambique, we have a Swedish International Development Agency projects where we did rapid mapping. At the time, the UN Humanitarian Aid Agency, they were on the ground, but they have no maps. We actually gave them the maps through the Swedish Embassy in Mozambique, and that was used during their relief operations. And then this is flood in Rwanda, near Kigali. We also have a CEDA project there. So the disaster management agency says, oh, we really need this data because, again, they have no control how much damage it is. They don't use too much technology there. Yeah, so with this urban mapping and monitoring, we're able to support a toolkit called EO toolkit for sustainable cities and human settlements. It's a collaboration between GEO group observations with UN Habitat. So we sort of put together data, tools, use cases, so that cities globally can use this to support monitoring of SDG. So some data sets we collected, and there are some challenges. I will not mention it here, but anyway, because of challenges, my team has decided to help to make a tool to automatically track the 11.3.1 land use efficiency, because the UN definition of cities are different. It's not administrative boundary, because Stockholm, maybe I have the image here. Stockholm, the city is inner city, very small inside. Beijing include all the mountains around it. So then you say, oh, Beijing is greener than Stockholm, but that's not correct, right? So that's why the UN adopted a global definition of cities based on the building density. But no one knows how to draw the boundaries, so we made an automatic app movers engine to draw the boundary automatically, and then looking at the land use efficiency. So then we, this app was collected in the EO4 SDG toolkit and also gave to UN Habitat, so that won us the EO4 SDG award. It's part of the Google Impact Award as well. So now I'm moving on to climate change and wildfires, looking at the wildfire, in Canada, there are many more fires, especially the area burned in Canada, United States are also growing, and the fire-urban interface, more buildings are included. So it has a lot of impacts on the global scale. Looking at the wildfires versus fossil fuel, you can actually see the wildfires making really a lot of contribution to the emission at a global scale. Let me see. Yeah, we're just comparing the data being used. So the one that changes the most is like every 10 minutes. You have an image that's from geostationary satellite. Then you have in the middle there, it's daily images or twice daily, day and night. Via Modis, Sentinel-3. Then you have images on the right-hand side, Sentinel-2, and the radar, Sentinel-1 below every few days. So these kind of data are really very useful, all of them, for tracking wildfires. So we're looking at a variety of scale. For active fire detection right now, the mostly used are the goals every few minutes, every 10 minutes. You can see the image to the right. So, but fire has to be large enough because it's kilometer resolution. On the left is the goals, on the right is the VIIRS image. Then it's 375 meter resolution that you can track fire. So we've been actually working with super resolution using generative models to say, okay, can we make higher resolution at 10, 20 meters out of these low resolution images? And for burn area mapping, it's going well, but for active fire, it's not very easy if you don't have a lot of active fire at high resolution as training level. So, but we are working on it. So yeah, just to show all these images again. So not only you have, resolution problem, you also have a lot of clouds problems. So yeah, just say the firefighting agency have been using this image mostly for contextual awareness. But I asked them, okay, what do you need? Anything, whatever that's available, because it's an emergency decision support. Anything you can produce, we will use. So that's why we have this multi-resolution, multi-modal Earth duration data for wildfire monitoring. So on the left side is the burn area mapping. You have the spatial temporal resolution, so mid resolution, coarse resolution. Mid is every few days, 10, 20 meters. Coarse resolution, we have 250 to 500 meter resolution. So mainly we use short-wave infrared, near-infrared, or short-wave infrared, mid-infrared, near-infrared. Mid-infrared is for heat or active fire detection. On the radar side, we have C-band, L-band. So I think, as I mentioned, clouds are a main problem, as you can see here. The image actually on the right below is California. Everybody thought about sunny California. We were very surprised to see actually a lot of clouds in California as well when you really needed the images. So basically, I took the Capella Space illustration where SAR company launching SAR satellites in California. So 50% nighttime, 50% clouds, you have very little visibility. So therefore, multi-modal data are really useful. So here we show both radar and optical image. You can see they both provide good information for burned area mapping, but radar doesn't really have good information right now for active fire detection, but it can detect burned areas. So on active fires, mainly we are relying on optical images. So here, just to show multiple resolution data for the Greek island fire, you can see from 1 meter planet to 370 meter resolution data for detection. We use all of them. So this is just illustration in Canada, how much cloud coverage it was for this Stanley Creek fire. 1 million hectares were burned just by one fire. I know that maybe you all know about it, but for the physical basis, for optical data, it's very easy, burn, unburned, and vegetation, non-vegetation, in near infrared, short infrared, when infrared, a big difference, and then you can easily detect this by VNVR or NVR. Then for SAR, it's more complex. A fire, then you either have tree burned, leaves, branches burned, but trunks are still standing, or you have completely burned down. Then you have also surface scattering from canopies underneath, surface scattering. So it's not very easy, but we're using the radar burn index that we developed for this kind of mapping. And it's not as obvious, but still burned and unburned, you can see some differences here. But it's very complex with SAR patterns of backscatter change. Can be, usually it's a decrease in backscatter, but can be increase in backscatter because of soil moisture conditions, especially if it rain after the burn. Therefore, it's not very easy. These are, let's say, examples of Canadian fires we've been used. As I mentioned, we have a data set from 2017 to 2024. Now we're adding 2025, and we hope we will release it by soon for Canada and United States. Then they have burned area polygons. In US, they even have burned severities. So these are very useful data set. So we also did some field work together with the British Columbia Wildfire Services as well, trying to collect ground truth data. Just quick overview of active fire detection. We use GOES as well as VIIRS, and then we were able to detect active fires quickly and also slightly better than the existing wildfire products, active fire products from NASA firms. And we also have developed methods for continuous monitoring with Sentinel-1, Sentinel-2, as well as VIIRS. So this is every few days. In Canada, it's basically every 2 and 3 days. For VIIRS, then we have every day, daily monitoring. So this just to show using SAR, you can actually get quite good development monitoring through clouds, because it's a large fire burn for 2 months, still very few optical images were captured. So just some more examples of different sites. This is Anton Hill, 200,000 hectares burned. This is in the US, I think. wildfire, and this is the Australia fire near Sydney, close to 1 million hectares burned, 2019. So yeah, so this recently we've been working with generative AI for daily high-risk wildfire monitoring. I mentioned slightly earlier. You have the Sentinel-1, Sentinel-1 data. You know, the bands are quite similar, but every few days, then we have the MODIS and the Sentinel-3 on a sub-daily or twice daily or daily basis. Currently we can only do super resolution for the day because we don't have night image from Sentinel-2. So then we can have daily by, you know, spectral bands are quite aligned. How can we create using the pre-image from Sentinel-2 and the near real-time image from MODIS, RIRS, or Sentinel-3 and generate the burn areas on a daily basis. So that's what we have been doing. We devised the method for fire super resolution DDPM. It seems to be working quite well. This is the Palisades fire in California in January last year. Maybe all of you. We used the Sentinel-2 pre-image and Sentinel-3 and MODIS. The burn area image, and we were able to generate quite good output. And this is Sentinel-2 post. That's after the fire. And the label, as you can see, our detection is slightly better than the label. The unburned areas were also detected. This is our distribution. We also tried in the group fire. The results are also quite good. Based on all this work, we developed a wildfire monitoring app. So basically, you have fire progression, and on a daily, low resolution, non-daily, every few days. Then you have critical infrastructure, human settlements. Then the wildfire services can decide where to protect, you know, buildings, human, and critical infrastructure. This is best good to support emergency response. And also for the future, we plan to add this ecosystem importance as well, environmental data to it, to say which ecosystem we should protect. Anyway, and now all of you are working on different areas of, you know, protecting our planet. So let's work together to protect our fragile but beautiful planet Earth. Thank you very much.
Thank you very much. We have quite a bit of time for questions. Typically, we do.
I have a question, not very related to the specific topic.
Yeah.
But I think you have been working in this field for quite a few decades.
Yeah.
And the main thing you have presented is mainly, I think, data-driven, you know, these neural network models. How have you seen like this shift of methodology in remote sensing and for monitoring these things?
Very good questions. Yeah, thank you. Actually, this is an excellent question. So when I started out at Waterloo doing my PhD, actually, I used the old like neural network. At the time, it's called artificial neural network. I took a course on artificial neural expert systems. Actually, it's a main course. Then I thought, oh, I should try this. So that was like, I don't know, 94 or something like that. So that had only 4 hidden layers, if I remember correctly. I implemented at the time for agriculture medicine, but it was working slightly better than other statistical models. So I had my first paper 95 on artificial neural network. But after that, it's a black box and very few people wanted to use it. So it has been, under the radar for quite many years until, let's say, 10, 15 years ago, it came back. So then in the remote sensing field, a lot of statistical models, machine learning, that's then, you know, random forest, SVM, you know, all this stuff have been popular, then came deep learning again. So I really see this time AI is revolutionized how we analyze Earth elevation data, especially like so much data. It's so many different satellites, especially I see the promise of foundation models. And because we don't have labels everywhere, how can we use foundation models and to help, especially to produce good data, good decision support for the global south, for data scarce regions. I think that's really important. Yeah.
So for all these applications that you've shown, often you utilize like the best custom-made deep learning models for the particular problem.
Yeah.
So I'm curious operationally, how computationally expensive is it to actually run these at scale? And how do you manage that when you're trying to build an operational product? If they're deep learning methods, and then also, yeah, are you thinking maybe that geospatial foundation models could help us reduce that compute in any way? How are you, what are you thought about that?
Yeah, thank you. Excellent question again. Yeah, so since the application I work with showed here are the really operational driven, so we have to really have limits to use as little computing resources as possible. So let's say the urban mapping, basically anyone use Earth Engine. The model is pre-trained on our local GPU clusters. So then you can deploy it anywhere on Earth Engine, but they don't have to do that. We just made the interface. So use very little. So Earth Engine is free if you're not a commercial entity.
For now.
So for now, yeah, we're a bit worried about the things. Yeah. So hopefully they still for good application, they don't do anything. So yeah, we're looking at alternatives, but usually we try to sort of minimize the commute. But the generative models right now is very computationally intensive. That's why it hasn't been used yet by anyone. But I think one of the students found a solution recently, but we're still testing it. So this doesn't work to give to users. So can we make something that's useful for users? So they're working on a light model now. Yes.
So to get the images, how many satellites do you need? And when you process the data, what do you divide the image into like small squares and process each square one by one?
Yeah, they are all for the deep learning model. They're all divided into pages. Yes.
And how many satellites do you need to measure all these data?
We for fire we use everything as much as possible. But for urban we only use 2 satellites, right? Sentinel-1, Sentinel-2, not too many.
Launched by you?
Planet, but that is sort of whatever that's open.
Are they launched by you? Those 2 satellites?
Pardon?
Are those 2 satellites launched by the EU?
No, yeah, Sentinel-1, 2 are completely free. Planet is not, but you can get open free data. You have a quota for a period, so if you don't exceed your quota, I got a permission for extra quota, so you can access quite a lot of free data.
In European space.
Yeah, you can just sign up for a contact Planet.
Yeah.
Thank you for your talk. I was wondering if ESA works with like local agencies from global south countries to like provide ground truth labels for the result of all the models that you're showing. Like, is there some sort of like proof of like a correct prediction in those areas where there was any training data?
Actually, I mean, we mostly let's say for urban, we actually don't get much data from the local area because we have hundreds, 200 sites.
Yeah.
So we try to use open data for that, the open labels. But for fires, we got from Canada, United States, their national database, right? So these are official labels. Yes, please.
I can follow on from that one. So,
Yeah.
for the tropics where fires burn only for a short time often, and then they green up very quickly again. And so they're quite hard to detect compared with the Canada and America, I'd say. Have you tried doing fire detection in the tropics yet?
Not yet. Actually, this is even requested by the Swedish Forest Agency because they said, oh, the changes you detect are more like drastic change, right? So we want to detect not just clear cuts or burn. We want to know these subtle changes. So that's exactly, it's quite challenging because a lot of clear cuts now in Sweden are thinning rather than big square clear cuts. So they want us to detect that. So we're working on it, but I haven't really got the best solution yet. But we are working with a forestry collaborator. They're using UAVs to capture every tree. I thought if we get hold of those kind of training data, plus the satellite data, we can detect every tree. Then that's problem will be resolved, but still probably doesn't help with tropics. Oh, it's so dense with the canopy, but for Sweden, it probably would work. Yes.
Maybe we're running out of time, so let me try and ask the last question, at least for this session. So, I mean, the way I see it, we're trying to understand what's happening on the Earth, and we have remote sensing through different satellite modalities. We have obviously planes flying over for planet, creating high resolution images. But we also have, more than 6 billion mobile phones which are gathering data. So citizen science, or just through Google Photos or whatever it is, and other kinds of data, non-traditional ground truth data, perhaps I should put it that way, on social media, for example. Do you have a vision of how we will integrate all of these different ways to see the Earth into one sort of unified view of what's going on? But that would be really understanding planet Earth.
Yes, that's an excellent suggestion. I think definitely we should use all available data. So this project finished last year, right? We just got a new flagship project from Digital Futures. It's called Urban Environmental Intelligence. So one of the things we're looking at is to use crowdsourced data. Let's say here I show this urban heat island. That is mostly people use land surface temperature as a proxy used by everybody, but that is not really a good way because tall buildings, you measure the top of the building, but in the shadow, it's actually not hot. So we are using the people volunteered, these weather stations from homes. So how do we link that with land surface temperature to produce air temperature? So in the urban environmental intelligence, we have several different aspects we're looking at. So definitely other type of data will be incorporated together with satellite data.
Great, thank you very much. Thank you for coming.
Yes, thank you.
But we do need to stop because the next.
I wonder if I can get a photo with all